theta equals pi by 2, and that will be L comma n proportional to gamma n factor is not going to be important anymore. And then there is this alpha integral. I'm calling all of this like together. I'm symbolizing this by integral with a subscript alpha. So that's what I mean, because its form is not going to be important. So we have the Euclidean integral now, j equal to 1 to n dl bar j, minus infinity to plus infinity, sum over k equals 1 to n alpha k, sum over kj lj bar, sum over k dki plus m square. You do not need minus I epsilon prescription because the purpose of I epsilon prescription is done. We have done the analytic continuation, and the Euclidean integration doesn't need that. So these are Euclidean momenta now. And these integrals, each one of them, these are integrals over d-dimensional Euclidean space. So let us look at this Euclidean integration. The entire region of integration is basically an L times d dimensional Euclidean space, because you see this is so there are n d dimensional integrals, and since it's an Euclidean space, they just add up the dimension. They become just n times d dimensional Euclidean space, and they are given by this L1, L bar 1, and their Cartesian components 1, then 2, and so on, L bar 1 d, then L bar 2 1 2, L bar 2 d. This way, L bar L 1 2 L bar L d. So these are the Cartesian coordinates of this LD dimensional Euclidean space, and there you can now consider a spherical polar coordinate. And that let us call k theta 1 to theta LD minus 1. There are LD minus 1 number of angular coordinates and one radial coordinate, which is k. And therefore the measure will be given by this product j equal to 1 to n dlj bar will be given by dk, then d theta 1 to d theta LD minus 1 times k to the power LD minus 1 from dimensional analysis. This is this is a length of LD dimensional length, and thetas are dimensionless, and therefore you should have dk times k to the power ld minus 1. For example, in 3 dimension, you have r squared dr times r squared, right? So net dimension should be 3. So that is the same here. And there will be a factor, theta dependent factor. And this is basically the Jacobian. This entire thing is the Jacobian factor coming from the coordinate transformation. Transformation between the Cartesian system and the spherical polar system. Okay. Therefore, now let us look at how this integral I L comma n, that's proportional to this alpha integral, and then there is an angular integral, and then there is this dk radial integral, k to the power ld minus 1 times sum over k alpha k minus n. Okay. Now, this integrand will have the angular dependence because of because there are certain fixed vectors, and we will have, if you expand this square, you will have dot products between L's and P's and L's and L's, between L and L and L and P. Those dot products will be dependent on angular coordinates. So this angular dependence due to dot products of L bar j with L bar j prime and P bar I. Now, if we take k to be large, so there is this entire integral, okay. If we take a region which is large value of k, then of course this dependence on p and m will drop out, because this contribution is so large that you can neglect them. So consider the region given by large k. And that will be ILN proportional to alpha integral angular, then dk lambda to infinity, k to the power ld minus 1 sum over k alpha k j a k j l j square to the minus n, plus of course contribution from other regions where lambda is much greater than mod p bar I m for all I. Okay, so I'm just separating out a particular portion of the entire result, and we'll argue that the divergence will come from that portion. Now consider a particular angular direction given by theta c1 to theta c LD minus 1 such that L1 bar 1 equal to all the components, all the Cartesian components that we talked about here, all of them, each one of them is equal, all of them are equal. So that's a particular direction in a three-dimensional space. If you take x, y, and z, all of them to be equal. In a two-dimensional space, if you take x and y to be equal, it's a line passing through origin, which is making a 45-degree angle with the axis, right? So it is that kind of a line in a higher dimensional space. Along that line, you are going a long distance. So in a two-dimensional space, if it would be two-dimensional space, then it is this line. Along this line, you are going to a long distance. Okay, that is k, right? So you choose this all Cartesian components to be same as k. Then since all these LJs are same, they will come, this value is k, it will come out, and you will get all these alpha dependent factors a prefactor. Okay. So L has come out and it has taken the form k to the power twice n. Of course, there are contributions from other region. But for large value of k, this is basically an integral of power of k. This is a power of k, this is a power of k. And therefore, this portion is like dk at large value k to the power LD minus 1 minus 2n. LD minus 2n minus 1. Now we define superficial degree of divergence omega to be d times L minus 2n. Okay, which means that if omega will be 0, dl minus 2n is 0, then it will be k to the power minus 1, and that integral will be logarithmic k with an upper limit infinity. So it will be logarithmically divergent. If it will be so similarly, if omega will be greater than 0, correspondingly this will be higher divergences, linear, quadratic, and so on. Okay. It's only when omega is negative that it is k to the power minus 1 minus something, and then it is convergent. So this is why it is called superficial degree of divergence. This is the definition of that. Okay.